So if we see that we have three equations with three unknowns and they're all linear, then they may come together just like this and actually sort of cross and meet just at one point, in which case there'd be one solution. That kind of system, a system where they all meet at one point, that's called an independent solution. I mean, independent system, rather. An independent system because they all come together and they meet at one point. The other possibility, like what we talked about just moments ago, would be that, let's see, these, I have to figure out how they come apart here. There we go. You have two coming together like this, but maybe, in fact, the third one comes together and meets just like that. Can you visualize that? It would look just like this. So, in fact, the solution now would actually be where they all three meet, would be a line of solutions. They all just touch on that line. And that would be called a dependent system, because, in fact, there are infinitely many solutions, all the solutions that are actually on that line. And then there's a final possibility, which is that, in fact, this plane, the third one, would be parallel to one of the other ones, like this. See, in this case, what would happen is, well, there's no solution where they're all satisfied at once, because they don't all touch at the same time anywhere. This would be called an inconsistent solution, an inconsistent system, and there'd be no solution. So we could have a consistent solution where, in fact, they all fit together, right, nicely to meet at one point, like this. Or you could have a solution where, in fact, they meet together at a lot of points, like this. Or you have a solution where, in fact, a situation where they don't meet at all. And that would be a independent solution, independent system, a non-independent solution or system, and then you could have one where, in fact, there's no solution, all inconsistent. Okay, anyway, those are just the names. Let's just watch out for them and make sure that we realize we could get one solution, we could get a whole line of solutions, or we could get no solutions. Okay, let's try an example. Here is our first system. Let's look at this one. X plus 2y minus z equals 1. And at the same time, 2x minus y plus z equals 6. And also, 2x minus y minus z equals 0. And I want to solve all those equations at the same time. So what do? Well, I'm going to sort of do an elimination method here. The trick is just to keep dividing and conquering, get rid of the variables, and just try to solve for one of them. So for example, here's what I notice. If I take these two equations right here, forget about that one. If I were just to add those two up right now, do you see what would happen? I'd get rid of the z here, because minus z and z would be 0. So if I took these two equations and just added those up, I'd see a new equation that would look like this. 2x and x would be a 3x. 2y minus y would be a plus y. And minus z plus z is 0. And 6 and 1 is 7. So do you see how I added these two equations up by themselves and I got rid of one of the variables? Now, what happens if I take these two equations and add them up? They're two different equations now. Well, they have one equation in common, I guess, but I'm introducing now this equation. If I add these two, notice that, in fact, the z's will drop out here too. So if I add these two, what will that give me? Well, 2x and 2x is 4x. Minus y and minus y is minus 2y. And plus z plus minus z drops out, and I'm left with equals 6. And see how I divided and conquered? I took this 3 equations in 3 unknowns, and by taking the equations at pairs at a time, I was able to now reduce it to 2 equations in 2 unknowns. And now I've reduced it to a problem I can solve. How would I solve this? Well, one thing I could do is take this last equation there and just divide it through by 2. And if I do that, I would see 2x minus y equals 3. So let me record these two equations right up here. So here I see 3x plus y equals 7. And then this equation, which was just this divided by 2, would be 2x minus y equals 3. And what do I notice? I notice that if I just add those equations up right now, the y's will drop out. Do you see how I keep eliminating a variable? Here I'd see a 5x, and that's 0, equals 10. And so therefore I see x equals 2. Neat, I just found the x intersection. What would y equal? Well, to find y, I can go back to any of these equations that just had an x and a y in it and plug in x and solve for y. So for example, if I put in x equals 2 right into here, what would I see? Well, I'd see 2 times 2, which would be a 4, minus y equals 3. So I can now solve this for y. If I bring the 4 over to this side, I'd see minus y equals negative 1, so y equals 1. So I just discovered y has to be 1. And I did that by taking one of the equations that just had x's and y's in it and replacing the x by 2 and solving for y. Okay, well, last up I have to find z. How do I do that? You pick any one of the 3 original equations, and the interesting thing is it doesn't make a difference which one you pick. You could pick this one, or this one. I'll pick the first one and just plug in the x and plug in the y and then solve for z. So I put a 2 in for x, a 2 in for y, but I have to multiply by 2, minus z equals 1. 2 plus 2 is 4, and so I see 4 minus z equals 1. If I bring this over, I see minus z equals minus 3, and so z equals 3. And so there's my solution. In fact, we have one of these systems that would be classified as an independent solution, because in fact they all meet up at one point, and the one point they meet up, that point right in there, turns out to be the point x equals 2, y equals 1, and z equals 3. That's a point they all share in common. So in fact, this is an independent system, and you can check and take these values for x, y, and z and see each of these are satisfied. My method was just to divide and conquer, always in life. Given a hard problem, reduce it back to an easier problem, and then solve the easy problems. Combine these two, got one equation, 2 variables. Same thing here, another equation, 2 variables, reduced it to something we can do, solved it, went back, found the last one. Okay, we'll take a look at another example coming up next.